Close your eyes for a moment. Not to sleep, not yet. Just to feel. There is water above you. You are well below the surface. The light that reaches you here is not white. It is the color of old glass. Green at its edges, blue at its center. It fades into nothing below your feet. The water has weight here. You can feel it pressing against you from every direction. Not painfully, not violently. It is more like being held. Like being wrapped in something ancient and unhurried. The pressure is even and complete. The temperature is cool. Not cold in the way of wind or ice. Cold in the way of deep stone. The kind of cold that has never been warm. The water carries dissolved minerals from the seafloor. Calcium, silicate, the slow chemistry of rock dissolving into ocean. This dissolving has lasted millions of patient years. If you could taste it, it would not taste like the sea you know. It would taste heavier, older, quieter. There is almost no sound. What sound exists comes through the water as vibration rather than noise. A low, distant frequency arrives in your chest before your ears. This is the sound of ocean on a geological scale. It is the sound of water that has moved without interruption. It has moved longer than any living thing has been alive to notice. Somewhere below you in the dimness, something is moving. You cannot see it clearly, not yet. Only a shape, a curve, a spiral. Perfect in its geometry, patient in its motion. You will understand what it is, in time. But first, we must begin at the beginning. The beginning is a rock face in Idaho. Dry air, desert light. The smell of dust and warm stone on a summer afternoon. A geology researcher kneels in front of a pale limestone cliff. She holds a brush. She clears sediment from something embedded in the rock. It does not look like it should be there. It is a spiral. A perfect, unbroken, mathematically precise coil of stone. It sits embedded in the cliff face naturally, like a knot in wood. It is roughly the size of a dinner plate. Its surface is smooth in places and ridged in others. The ridges follow the arc of the coil with absolute regularity. One after another, evenly spaced, like the teeth of a comb bent into a circle. It is beautiful in a way that is slightly unsettling. You know, looking at it, that it is not a shell. It is not a coral formation. It is not a geological accident. It was grown by something alive. Something that used this coil as a tool for eating. Hold that spiral in your mind. Now expand it. The animal that carried this spiral was not small. Estimates based on the size of the tooth whorl place the largest individuals between 6 and 7.5 meters. That is roughly the length of a city bus, from the front door to just past the halfway point. Long enough that if it held still in the water, you could walk its full length in 10 steady steps. It moved through water with the patience of something that has never needed to hurry. Its body was broad at the front, tapered toward the tail. Wide, flat pectoral fins held it stable near the head. At the very front of that body was the spiral. Curved forward and downward, pale, precise, impossible. A geometric argument for the strangeness of life. It is tempting to call it a monster. We have a habit of doing that with things that are old and large, and built differently from us. We look at the spiral jaw of Helicoprion and reach for words like terrifying, nightmarish, primordial. We surround it with dramatic music and dramatic lighting. We make it a creature of darkness. But that is not what it was. It was an animal. It breathed water through gills the way every fish has ever breathed. It followed temperature gradients in the ocean, the way every aquatic predator follows warmth in prey. It grew slowly over years, adding teeth to its spiral one at a time. Its jaw expanded as its body lengthened. It had parasites probably, it had injuries. It had moments of stillness in deep water when the hunting was poor. The energy cost of moving was sometimes greater than the energy available. It was not a force of darkness. It was a living thing, navigating a living world. It had no awareness of its own strangeness. It did not know that its jaw was unusual. It did not know that 270 million years after its death, a human being would kneel in the Idaho dust. That person would stare at the fossilized remnant of that jaw. She would carry an expression caught between confusion and wonder. The animal simply lived and ate and moved through the water. And then, as everything does, it stopped. The strangeness of Helicoprion is not that it existed. The strangeness is that it existed for so long, through so much change, in a world that was itself constantly in the process of becoming something else. To understand what it was, we have to understand where it lived. And when. To do that, we have to leave this desert behind. We have to leave the dry air and the pale limestone cliff. We leave the sound of wind moving through scrubland. We have to go back. There is a version of the past that we can visit. Not physically, not with any machine or instrument we currently possess, but through language and through the slow, careful accumulation of evidence, we can reconstruct a world. Paleontologists, geochemists, and CT scan technicians have built this evidence across decades of patient work. We can describe its water temperature. We can describe the chemistry of its air and sea. We can describe the creatures that lived in it with enough specificity to make the world navigable. That is what we are going to do. To understand Helicoprion, we must leave the human world behind entirely. We must set aside the desert and the museum and the research paper and the documentary camera. We must enter a time before any of those things existed. Before mammals existed. Before the first dinosaur had taken its first breath. We must go back to a time when the ocean covered most of the earth. When the continents were gathered together in a single great landmass. When the sea was warm and dense. It was populated by shapes that were almost familiar, almost recognizable, but not quite. Not quite. The journey begins now, and it begins slowly, as all the best journeys do. Welcome to Info Jungle. If you enjoy calm, thoughtful documentaries about the natural world, consider subscribing. These videos are created to help you relax while learning at a gentle pace. Every episode takes you somewhere different. Every episode takes you somewhere deep. Now let us continue. The first Helicoprion fossil was not found in Idaho. It was found in the Ural Mountains of Russia. A Russian geologist named Alexander Karpinski described it in 1899. He was examining a collection of marine fossil material when he encountered the spiral. He knew immediately that it was the tooth structure of some large ancient fish. What he could not determine was where on the animal's body the spiral was located. That question would remain open for more than a century. This was not a simple question. The spiral is not a small structure. It is a substantial piece of calcified dental material, dense and well-preserved. It coils tightly in on itself. Karpinski had the spiral, but the rest of the animal had long since dissolved. Helicoprion, like all members of its lineage, had a skeleton made of cartilage rather than bone. Cartilage decays. It leaves almost nothing behind in the fossil record. The spiral survived because it was composed of dentine and enameloid. These are harder, denser materials, the same basic substance as teeth. Everything else vanished into geological time. So Karpinski had a spiral and nothing else. And the debate that followed was, by the standards of paleontological disagreement, fairly remarkable. Over the following century, researchers proposed many different locations for the tooth whorl. Some believed it sat at the tip of the lower jaw, protruding forward like a saw. Some suggested it was positioned on the upper jaw. Others proposed it was tucked beneath the body, used to rake the seafloor for prey. One notable theory placed the spiral on the tail, suggesting it was used for defense rather than feeding. The drawings produced across this century of debate are genuinely extraordinary to look at. Each one depicts a real animal, drawn by trained professionals, based on genuine fossil evidence. And yet each one looks subtly or dramatically wrong in ways that are sometimes difficult to articulate. The animal was real, the spiral was real. But without a complete skull, without any cartilaginous material, without the skeletal architecture that would anchor the spiral, the question remained open. For 114 years. Then, in 2013, a team of researchers at the Idaho Museum of Natural History used CT scanning technology. They examined a particularly well-preserved Helicoprion specimen. The scan revealed something invisible to every previous researcher. It showed the faint but unmistakable impression of cartilaginous jaw material preserved within the surrounding rock matrix. Not the cartilage itself, which had dissolved completely, but the chemical shadow of it, the shape of the space where it had been. And that shape told the story. The spiral sat in the lower jaw, fully within the mouth. The upper jaw had no teeth at all. It was a smooth cartilaginous surface that pressed down against the coil from above. When the animal closed its mouth, the spiral did not simply clamp down. It rotated slightly inward, drawing material caught between the teeth toward the back of the throat. A biological ratchet mechanism, a one-way conveyor built from 180 rotating teeth. 114 years of disagreement, resolved by a machine that didn't exist for most of that time. The fossil had been waiting patiently, as fossils do. The name Helicoprion means spiral saw. It was named for the most obvious thing about it. The spiral saw was its defining feature. For most of the history of its study, the spiral was also its central mystery. But understanding what Helicoprion was requires looking past the spiral for a moment. It was not a shark. This is a common misconception, and an understandable one. Helicoprion superficially resembles a large shark. It was a large marine predator. It had a cartilaginous skeleton. It moved through open water. It had the general body plan of a shark, elongated, streamlined, fin-stabilized. But taxonomically, it belongs to a separate lineage. Helicoprion was a member of the order Eugeniadontida. This is a group of cartilaginous fish that shared a common ancestor with sharks, but diverged from them early in evolutionary history. Its closest living relatives are not the great white shark or the hammerhead. They are the chimeras, also called ratfish or ghostfish. This is a quiet, deep-dwelling group of cartilaginous fish. Today they inhabit cold, deep ocean environments around the world. Chimeras are not famous animals. They do not appear in documentaries about apex predators. They move slowly. They feed on hard-shelled invertebrates, which they crush with flat, plate-like teeth. They have large eyes adapted for low light. They carry a long, tapering tail. They look, in some lighting, like something drawn by a child attempting to draw a shark from memory. Correct in broad outline, subtly wrong in every specific. They are also, by most accounts, rather gentle animals. Slow-moving, deliberate, uninterested in confrontation. If Helicoprion behaved anything like its modern relatives, the picture that emerges is not of a frenzied predator. It is of a patient, methodical animal, moving through mid-water with quiet efficiency, sensing its prey through electroreception before it could see it, closing the distance slowly, opening its jaw, and closing the spiral around whatever soft-bodied creature had the misfortune of drifting into range. The eugeniodontid lineage as a whole was ancient even by Permian standards. Their origins trace back to the Carboniferous period, more than 300 million years ago. Helicoprion itself appears in the fossil record around 290 million years ago. It persists, remarkably and stubbornly against significant geological odds, until somewhere between 250 and 252 million years ago. The specific end date is uncertain. But what is certain is this: Helicoprion survived long enough to encounter the greatest extinction event in the history of multicellular life on Earth. It survived the late Carboniferous, the early Permian, the middle Permian. It survived shifts in ocean chemistry and temperature. It survived the slow rearrangement of continental landmasses. These changes altered current patterns and nutrient flows in ways that devastated many of its contemporaries. It persisted for somewhere between 10 and 15 million years. In the context of human history, 15 million years is a figure so large it becomes meaningless. Modern humans, our species, Homo sapiens, have existed for approximately 300,000 years. The entirety of recorded human civilization occupies roughly 5,000 years of that. Helicoprion existed for 10 to 15 million years. It observed, without observing, without any awareness of observing, an expanse of time 50 times greater than the full duration of our species. And it was not even the oldest thing in its ocean. The world of Helicoprion is almost incomprehensible in its difference from our own. Begin with the continents. We are accustomed to a world of 7 separate landmasses. They are distributed across a planet with 2 distinct polar ice caps. There are 5 named oceans and a relatively stable arrangement of mountain ranges and river systems. This arrangement has characterized the Earth for the duration of recorded human memory. None of that existed in the Permian. In the late Carboniferous and early Permian, when Helicoprion first appeared, the Earth's landmasses were completing a slow collision. Over tens of millions of years, tectonic movement had been drawing the scattered continents toward one another. It closed ancient oceans and built new mountain ranges at the points of contact. The result by the early Permian was Pangaea, a single supercontinent, a landmass so large that its interior regions were hundreds of miles from the nearest coastline. Those interior regions were dry, hot, and almost completely lifeless. The supercontinent was surrounded by a superocean. Panthalassic, the name means all sea. It covered approximately 70% of the Earth's surface. An expanse of open water so vast that if you positioned yourself at its center, the nearest shore would have been further away than the Moon is from the Earth today, measured in travel time across water. But Helicoprion did not live in the center of Panthalassa. It lived along the margins, the continental shelves, the shallow coastal waters of Pangaea, and the island chains and reef systems that dotted the ocean's interior. These shallow regions were warm, nutrient-rich, and lit by strong equatorial sun. They were among the most biologically productive environments that have ever existed on this planet. The water temperature in these shallow seas averaged somewhere between 22 and 26 degrees Celsius at the surface, warmer than the modern tropics in some regions. The atmosphere contained higher levels of oxygen than today, though declining from the spectacular highs of the Carboniferous. The carbon dioxide concentration was rising, slowly, imperceptibly on any human timescale, but measurably across geological time. The sea itself teemed with life, in a way that is difficult to describe without reaching for the language of excess. The seafloor of the shallow Permian Ocean was carpeted with organisms. Crinoids extended their feathery arms into the current to filter passing nutrients. They covered vast areas of the bottom like an underwater meadow. Among the crinoids lived brachiopods, shelled filter feeders that had existed in essentially the same form since the Cambrian, 500 million years earlier. Between them, ammonoids moved in slow spiraling paths through the midwater column. These were coiled, shelled cephalopods, and among the most common Permian fossils. The ammonoids are important. They will come back. Above the seafloor communities, in the sunlit and mid-depth zones, swam creatures recognizable as fish but wrong in a specific Permian way. Recognizable in their general shape, torpedo-bodied, fin-stabilized, gilled, but armored in some cases, or carrying jaw structures that no modern fish possesses. Some were scaled in materials that have not existed in any living lineage for 250 million years. This was the world that produced Helicoprion. That sustained it, that fed it. That gave it 10 to 15 million years of uninterrupted existence in warm, productive, crowded seas. And then slowly, over centuries and then millennia, this world began to change. We will return to that change in time. For now, the water is still warm. The crinoids are still swaying in the current. The ammonoids are still moving in their patient spirals through the middle depth. And somewhere below us, something large and quiet is beginning to rise. Let the modern world go. Let it go the way you let go of the day's last thought before sleep reaches you. Not dramatically, not all at once. Simply allow it to recede. The dry air of the Idaho desert, the pale limestone cliff, the sound of a researcher's brush against ancient stone, the hum of a CT scanning machine in a museum basement. Let it all move away from you. What remains is water. What remains is the Permian Ocean. It is neither warm nor cold in a simple sense. It carries the temperature of its depth in layers. Warmer near the surface, where sunlight still touches it. Cooler as you move down. At the deepest points, the temperature approaches something close to permanence. A stable, ancient cold that has no memory of the surface and no interest in it. The light here has changed. It is no longer white. It is not the clean, neutral light of a museum room or a documentary studio. It is green at the edges of your vision and pale blue toward the center. Below you it fades into a green-gray opacity that has no bottom you can identify. The light moves. It shifts in slow columns as currents pass between you and the surface. It is not quite enough light to see clearly by, but it is enough to sense shapes. And there are shapes here. Slow-moving shapes, patient shapes. shapes that have been moving through this water since before anything on land had learned to breathe air. Your breathing slows. Your thoughts slow with it. You are not falling, you are descending, which is different. Falling is sudden and involuntary and frightening. Descending is gradual and deliberate, and after the first moment of adjustment, remarkably comfortable. The water holds you. The Permian Ocean holds you. And somewhere below the crinoid meadows, below the spiraling ammonoids, below the shifting green-gray light, something is moving toward you. Not quickly. It does not need to move quickly. It has all the time in the world. The first thing you notice is the color of the light. In the modern ocean, the one you know, the light has a particular quality. It is blue. Clean blue. The blue of a swimming pool or of the sky on a clear morning in October. It is a familiar color. A color that has been in human experience for as long as humans have existed. The light in the Permian Ocean is different. It is not blue in that familiar way. It carries more green in it. Not the bright, saturated green of tropical shallows. A deeper, quieter green, the color of old bottle glass held up to a weak sun. The color of water that contains different things than modern water contains. Different chemistry, different suspended particles, different biology doing different things with the light. Scientists who study ancient ocean environments can reconstruct this light quality from the chemistry of fossil pigments, from the preserved remnants of ancient phytoplankton, whose photosynthetic molecules leave chemical signatures in sedimentary rock. These signatures survive even after hundreds of millions of years. The Permian shallow ocean, based on this evidence, had a spectral quality meaningfully distinct from modern tropical shallows. Warmer in its color temperature near the surface, shifting toward a murkier, mineral-filtered quality as depth increased. Standing floating in this light, the difference is subtle but persistent. Something is slightly off, not wrong, not threatening, simply not quite what you know. The water itself feels different against your skin. The salinity of the Permian Ocean was broadly similar to modern oceans. The chemistry of saltwater is constrained by geology in ways that don't change dramatically over time. But the specific mineral content was different. Silicates from the seafloor in higher concentrations. Calcium carbonate from the vast shellfish communities near the surface, constantly dissolving and precipitating. The water has a slight weight to it that is difficult to articulate precisely. It feels denser than water should feel, more present. The temperature at the surface is warm, noticeably warm. Warmer than a comfortable bath, but not uncomfortably so. This warmth comes from a combination of factors. The equatorial positioning of much of the Panthalassic shallow shelf. The greenhouse gas concentration in the atmosphere above. Elevated CO2 levels trapped solar energy with slightly more efficiency than modern conditions allow. The absence of polar ice caps large enough to drive cold, deep-water circulation. In the Permian shallow sea, the thermocline sits at a different depth than in modern oceans. The warm layer goes deeper, the cold layer begins further down. In between, the water moves in currents that carry heat from the equatorial regions outward toward the poles. These patterns are broadly similar to modern circulation but slower and warmer at every point. This is not a hostile environment. It is, by any biological measure, a rich one. But it is not the ocean you know. And the longer you remain in it, the more clearly that difference asserts itself. Not dramatically, not all at once. Just persistently. like the low-frequency hum beneath everything. Look up. The surface of the Panthalassic Ocean is perhaps 30 meters above you. The light reaches you from that surface in long, slanting columns. They shift and reorganize as the swell moves above. Each column of light is slightly different from the ones beside it. Slightly different in angle, slightly different in intensity. This depends on the thickness of the water it has passed through. Because the organisms are everywhere, the water column here is not empty between its visible inhabitants. It is filled, invisibly filled, with phytoplankton in concentrations that would color the water in patches of pale brown and rust red if you could see them from above, with zooplankton drifting in slow clouds through the sunlit zone, with larvae suspended in the water column in their millions. These are the juvenile stages of every shellfish, every crinoid, every brachiopod on the seafloor below. They are carried by current, filtering nutrients, growing imperceptibly toward their adult forms. This productivity is the foundation of everything. Every large animal in this ocean is sustained by this invisible abundance. The ammonoids feed on zooplankton, the fish feed on ammonoids, the larger fish feed on smaller fish. And somewhere at the upper reaches of this pyramid of consumption, patient and slow-moving and electrically sensitive, is Helicoprion. But we are not there yet. Look around you at the shelf environment itself. The seafloor, 50 meters below, is visible from here only as a suggestion of texture. A slightly darker zone, where the green-gray opacity thickens into something closer to brown. But you can sense its character even from this distance. The Permian Reef, if reef is even the right word, was not built from coral. Coral as we know it, the calcium carbonate structures built by colonial polyps, was not the dominant reef builder of the Permian. The Permian Reef was constructed primarily by bryozoans. These are colonial filter-feeding animals that built branching, calcified structures. Calcareous sponges and siliceous sponges also built rigid frameworks from silica drawn directly from the seawater. The result was a reef structure softer in outline than a modern coral reef. Less vivid in color, more porous, more varied in texture. Where a modern coral reef presents a wall of bright, dense biological color, the Permian Reef presents something more like a forest. Pale, branching structures in cream and gray and faded amber, with spaces between the branches large enough to swim through. Between and around the reef structures, the crinoids. Crinoids in the Permian were everywhere. They are sometimes called sea lilies, and the name is apt. They look from a distance remarkably like flowers. A slender stalk anchors to the seafloor or to a piece of reef structure. At the top of the stalk, a crown of feathery arms extends into the current. Each arm is lined with smaller structures called pinnules. Each pinnule is lined with tiny tube feet covered in mucus. The current brings food, the tube feet catch it. The food moves down the pinnule toward the central mouth. The crinoid doesn't move. It doesn't need to move. The ocean brings everything to it. In the Permian, crinoid meadows covered enormous areas of the shallow seafloor. Not in meters, in kilometers. They formed dense biological carpets through which the current moved in modified, slowed patterns. They were habitat for hundreds of other species. Small fish sheltered between the stalks. Small invertebrates lived as commensals on the arms. Parasites, predators of those parasites. Entire small ecosystems operated within the larger ecosystem of the reef. The Permian Sea is not an empty stage waiting for its central performer. It is a fully populated world, rich, complex, layered with life at every scale. Helicoprion moved through this world the way a whale moves through a modern ocean. Present but not dominant, large but not solitary in the ecosystem. More like the visible tip of an enormous biological structure that extends in every direction, connected to everything around it by chains of consumption and competition and occasional cooperation. Somewhere above this reef in the middle depth, the current carries a shape. Long, deliberate, moving toward us at a pace that suggests it is not hunting right now. Just moving, just crossing the water from one place to another, with the unhurried efficiency of an animal that has no predators large enough to make hurrying necessary. It appears from the green-gray opacity at the edge of your vision. Not dramatically, there is no sudden movement, no displacement of water that announces its arrival. One moment, the middle depth is empty of anything large, populated only by the slow drift of ammonoids and the occasional small fish. And then, without transition, there is a shadow where there wasn't one before. It is larger than you expected. Not because you didn't know the size, the numbers were clear. 6 to 7 meters, the length of a city bus's front half, those numbers were accurate. But numbers, even accurate ones, do not prepare you for the reality of a living animal that large moving through water 20 meters away. The shadow resolves slowly into a shape. The body is elongated and broad at its front quarter. It tapers through the midsection toward a tail that moves in long, slow lateral sweeps. Each sweep of the tail moves a volume of water large enough to generate a pressure wave. You can feel it from this distance, not as wind, but as a slow thickening of the water around you. A momentary increase in pressure that moves through you from front to back and then dissipates. The pectoral fins are wide and held slightly angled. They provide lift and stability, the way the wings of a gliding bird provide lift. The animal is not swimming energetically, it is gliding, using the buoyancy of its body and the angle of its fins to maintain depth with minimal muscular effort. The tail sweeps are widely spaced, one every 4 or 5 seconds. Between sweeps, the body holds its position in the water. Only small, continuous adjustments from the fins keep it in place. It is profoundly calm. The word that comes to mind watching it is not terrifying. It is not monstrous. The word that comes to mind is ancient. Not in the way that word is sometimes used carelessly to mean simply old. Ancient in the way of something that has been doing exactly this precise motion through water of this precise temperature, for so long that the motion and the water and the animal have become indistinguishable from one another. It belongs here in a way that nothing can belong somewhere, unless it has been there long enough for belonging to lose all self-consciousness. Then it turns. Not toward you. The turn is gradual, a banking motion, like an aircraft adjusting its heading. The body rolls slightly to one side as the pectoral fin on that side dips and the other rises. As it turns, you see its profile for the first time. And the profile contains the thing you have been waiting to see. At the front of the lower jaw, extending slightly forward and curving downward in a smooth arc, the tooth whorl catches the available light. It is not as dramatic as you might have imagined. In the light of the Permian shallow shelf, at this distance, the spiral appears as a pale curve, a crescent of slightly lighter material against the darker underside of the animal's head. The individual teeth that compose the spiral are not individually visible from here. The whole structure reads as a single smooth shape, a curve that is both part of the animal and somehow separate from it, a mathematical object that happens to be made of biology. The animal continues its turn. The tail sweeps once, twice. The shadow lengthens as it crosses in front of a column of filtered light from the surface. And then it moves on, continuing in whatever direction the water and the electroreceptive sense of distant prey is drawing it, leaving the space it occupied exactly as it found it. Water in the same temperature, the same pressure, the same quiet opacity, as if it was never here. Except for the slow dissipation of the pressure wave its tail left behind, moving outward through the water in every direction, growing weaker with distance, until it fades entirely into the ambient vibration of the Permian Sea. To understand the tooth whorl, begin with the problem it solves. Every predator in every ocean faces the same fundamental challenge. It must convert prey into nutrition efficiently enough to sustain its body, grow its tissues, and eventually reproduce. The mechanism by which it does this is shaped by the specific prey available in its environment. The tool is built by the prey. Over evolutionary time, across thousands of generations of selection pressure, the jaw of any predator is a record of what it has been eating. The tooth whorl of Helicoprion is a record of soft things. Not hard-shelled prey, not armored fish or thick-shelled brachiopods. The geometry of the spiral and the specific morphology of the individual teeth that compose it points strongly toward soft-bodied or lightly shelled prey. The teeth are not broad and flat, optimized for crushing hard shells. They are not serrated and recurved like the teeth of a modern shark, optimized for cutting through large prey. They are conical and pointed and slightly curved inward. They are designed to penetrate soft tissue and hold it in place. Combined with the spiral arrangement, the functional picture becomes clear. Imagine the jaw closing around a soft-bodied cephalopod, a squid-like animal of moderate size, moving slowly through the water column. The tooth whorl makes initial contact. The pointed teeth penetrate the body wall. As the jaw reaches maximum closure, the spiral rotates slightly inward. This rotation is drawn by the mechanical action of the jaw closing. It pulls the prey toward the back of the throat. The upper jaw, smooth and cartilaginous, presses down from above, providing counterpressure. The prey cannot move backward against the inward rotation of the spiral. It cannot escape sideways because the jaw has enclosed it. It can only move in one direction, inward. The system is a one-way mechanism, a biological ratchet, a conveyor belt made of 180 individually growing teeth, arranged in a perfect logarithmic spiral. The logarithmic spiral is not accidental. It is one of the most common geometric forms in biology. It appears in nautilus shells, in the arrangement of seeds in a sunflower, in the spiral of a galaxy viewed from above. The logarithmic spiral has a specific mathematical property. Each successive coil is proportionally larger than the one before it, by a constant ratio. This means the spiral can grow continuously, adding new material at the center, without changing its fundamental shape. The outermost coils of a large spiral look exactly like the outermost coils of a small one, just scaled up. For Helicoprion, this property was essential. New teeth formed at the base of the spiral, the innermost point, throughout the animal's entire life. As each new tooth formed, it pushed the existing teeth outward along the curve. The oldest teeth, the first ones the animal ever grew, were at the outermost tip of the spiral. The newest teeth were at the center, actively in use. The animal never lost a tooth. Every tooth it had ever grown was still present, archived in the spiral in perfect chronological order, from outside to inside. The outermost teeth, worn smooth by decades of use, were the oldest. The innermost teeth, sharp and new, were the most recent. The tooth whorl was not just a feeding mechanism. It was a record, a biological journal written in mineralized tissue of every year the animal had been alive. The way Helicoprion moved through water tells us something important about what kind of animal it was. Movement is expensive in biological terms. Every movement requires energy. Every movement that is more energetic than it needs to be wastes energy. That wasted energy could have been used for growth, reproduction, or surviving the lean periods when prey is scarce. Over evolutionary time, animals tend to move as efficiently as their ecological niche permits. Fast animals are fast because their prey is fast, or their predators are fast. Slow animals are slow because their prey is slow, or their defense strategy doesn't require speed. The energy savings of moving slowly compound into significant biological advantages over a lifetime. Helicoprion, based on its body plan and its closest living relatives, was a slow animal. Its body proportions suggest low-speed cruising rather than high-speed pursuit. The pectoral fins, positioned close behind the head and oriented for stability rather than acceleration, are characteristic of animals that cruise at moderate depth. The tail, while powerful enough to generate significant thrust, was not built for explosive, high-acceleration swimming. It was built for sustained, efficient, low-energy locomotion across large areas of water. Modern chimeras, the closest living analogs we have for Helicoprion's movement style, are excellent swimmers in the sense of being efficient rather than fast. They undulate their large pectoral fins in a motion sometimes described as flying through water. They cover substantial distances with minimal apparent effort. They are capable of bursts of speed, but rarely use them. They navigate the deep ocean with the patient, methodical efficiency of animals optimized for endurance rather than sprint. Helicoprion almost certainly moved in a broadly similar way. Long, slow transits through mid-water, pectoral fins doing much of the work. Tail providing supplementary thrust and directional control. Body held relatively rigid, not the whole body undulation of a modern shark. The more controlled, fin-driven locomotion of a ratfish. Periods of gliding on the slight negative buoyancy of its cartilaginous body. Occasional depth adjustments driven by changes in prey distribution or water temperature. It covered its territory methodically, not urgently. There is something meditative about the movement pattern this reconstruction implies. An animal moving slowly and continuously through large volumes of water, sensing the electromagnetic signatures of prey organisms at distances of several meters, adjusting its heading with small, almost imperceptible changes in fin angle, not rushing, not reacting to sudden movement or sudden danger, simply searching, continuously, patiently, in the specific way that an animal searches when it has been doing the same thing for millions of years. When it has optimized every aspect of the process to the point where the search itself requires almost no conscious direction. The way breathing requires no conscious direction. The way a heartbeat requires no conscious direction. An automatic life, moving through automatic water. The ammonoids. We mentioned them earlier. They were important then. They are important now. Ammonoids in the Permian Ocean were extraordinarily diverse and extraordinarily abundant. They were cephalopods, relatives of the modern nautilus, and more distantly related to squid and octopus. Their shells were coiled in tight spirals. A different kind of spiral from Helicoprion's tooth whorl, but a spiral nonetheless. The inside of the shell was divided into chambers by curved walls called septa. The animal lived in the outermost, largest chamber. The inner chambers were filled with gas, providing buoyancy. By adjusting the gas and fluid content of these inner chambers, the ammonoid could control its depth in the water column with precision. They ranged in size from less than a centimeter across to, in some species, more than a meter in diameter. They fed on zooplankton, on small fish, on whatever the current brought within reach of their grasping tentacles. They were midwater animals, occupying the same depth zones that Helicoprion preferred. They were present in enormous numbers. Ammonoid fossils are among the most common Permian marine fossils found worldwide. This gives some indication of how dense their populations were in life. They were, in short, an ideal prey organism for Helicoprion. Moderate size, soft body behind a thin, crushable shell. Slow-moving or stationary for significant periods. Present in large numbers in the exact depth zones Helicoprion frequented. The hunting sequence would have begun with detection. Helicoprion possessed electroreceptive organs, the ampullae of Lorenzini, or their evolutionary equivalent. These could detect the weak electrical fields generated by the muscle activity of living organisms. Every living thing produces a small electrical signature simply by being alive. Every muscle contraction, every heartbeat, every movement through the water. At close range, these signals are detectable by the right sensory apparatus. Helicoprion's sensory apparatus was right for this purpose. Moving through the water column, it would have detected the electrical signature of an ammonoid at a range of perhaps a few meters. Not further, the electrical signals of a relatively small invertebrate attenuate quickly through seawater. But a few meters is enough for an animal moving at slow cruising speed. The heading adjustment required is small. The approach can be made gradually, without the burst of acceleration that would send pressure waves through the water and alert the prey. The ammonoid, for its part, would have had limited ability to detect the approach. It had eyes, moderately well-developed eyes, similar to those of a modern nautilus. But its vision in the murky midwater column was limited. Its escape response, when triggered, consisted primarily of rapid jet propulsion. Expelling water from its siphon could propel the shell backward in a sudden burst. This response could carry an ammonoid a meter or two in a fraction of a second. Effective against slower or less perceptive predators. Potentially less effective against something that had already closed to within touching distance before the prey detected it. The jaw opens. The spiral catches the edge of the shell. The conical teeth penetrate the thin outer whorl of the ammonoid's shell and the soft tissue of the mantle beneath it. The jaw closes. The spiral rotates inward. The ammonoid does not escape. It is not a violent scene. There is no blood dispersed dramatically through the water. There is no struggle of significant duration. It is quiet, efficient, complete in a few seconds. The prey becomes part of the predator. The predator continues moving through the water. The whole sequence, detection, approach, capture, consumption, has probably consumed less than 30 seconds. Helicoprion does not pause to rest afterward. It continues searching, electroreceptors still sweeping the water around it, fins still making their small, continuous adjustments, tail still sweeping its slow lateral arcs. The water closes behind it. The empty shell of the ammonoid drifts slowly toward the seafloor. Helicoprion was not the only large predator in the Permian Sea. This is worth stating clearly. There is a tendency in documentary treatments of any specific prehistoric animal to present it as the dominant force in its ecosystem, the apex, the unchallenged ruler of its domain. The reality of Permian marine ecology was considerably more complex and considerably more crowded. The Permian Ocean had many large predators. Some were cartilaginous fish, like Helicoprion itself. The xenacanthus sharks were a diverse group of cartilaginous fish that had been present since the Carboniferous. They were still present in the early Permian, though declining. They were generally smaller than Helicoprion but more agile, built for faster pursuit. Their teeth were different, bifid or two-pronged, suggesting a diet that included fish and soft invertebrates. They occupied slightly different ecological niches, but their ranges overlapped with Helicoprions in the shallow shelf environments. There were large bony fish as well. Actinopterygians, ray-finned fish, the group that includes most modern fish, were diversifying rapidly through the Permian. Some reached substantial sizes. Their bodies were more rigid than cartilaginous fish, their movements faster and more precise. They competed with Helicoprion indirectly, competing for the same ammonoid and cephalopod prey. There were also the edistids, relatives of Helicoprion within the eugeniodontid lineage. Animals like Edistis had a different tooth arrangement. Large, blade-like teeth in both upper and lower jaws formed a single cutting edge like the blades of scissors. Edistis was likely more aggressive in its hunting style. Its jaw morphology suggests it may have attacked larger, faster prey by slashing rather than engulfing. Whether Helicoprion and Edistis ever occupied the same waters at the same time is uncertain. Their temporal ranges overlap, but their geographic distributions may have been different enough to reduce direct competition. And then there were the things we don't know about. The Permian fossil record, while rich in some types of organisms, is less complete for large predatory fish. Their cartilaginous skeletons left almost nothing behind. We know Helicoprion existed because of its tooth whorl. But how many other large cartilaginous predators moved through the same water and simply vanished from the record, as if they had never existed? The honest answer is, we don't know. The Permian Ocean was probably more complex and more populated at its upper trophic levels than our fossil record allows us to fully reconstruct. What we can say is this: Helicoprion was large enough, and its jaw mechanism effective enough against its preferred prey, that it occupied a secure position in the Permian food web. It was not the only apex predator. It was not necessarily the largest animal in its ecosystem, but it was persistent. Helicoprion fossils have been found on every major continent except Antarctica. This suggests a nearly global distribution in the Panthalassic shallow shelf zone. It was successful enough to maintain that near global distribution for 10 to 15 million years. In any ecosystem, persistence is the truest measure of success. Helicoprion persisted, while other lineages rose and fell around it. While the ocean temperature fluctuated, and the sea level rose and dropped and rose again. While Pangea continued its slow, grinding internal adjustments. While the atmosphere above changed its chemical composition degree by invisible degree. Helicoprion persisted, moving through its changed and changing world with the same slow, patient, electroreceptive efficiency it had always used. Searching, always searching. The water is growing heavier around you now. Not from pressure, not from depth. From time. You are deeper in the Permian now than you were an hour ago. The surface, the museum, the desert, the CT scanning machine, the limestone cliff is very far above you. The light from the surface reaches you here as a pale, diffused suggestion of illumination rather than true light. The crinoids below you move in the current with their characteristic slow patience. The ammonoids drift in their spiraling paths. And somewhere in the green-gray opacity at the edge of your awareness, the shadow moves. Unhurried. Inevitable. Still searching. The light is different here. You notice the shift gradually. The way you notice the light changing in a room when the sun moves behind a cloud. Not a sudden darkening, but a slow, even withdrawal of warmth from the air. The green at the edges of your vision has deepened. The blue at the center has cooled into something closer to gray. The columns of light from the surface that were clearly defined in the shallower water above have diffused here. Not bright, not truly opaque, something in between. A permanent, patient dimness. The seafloor is closer now. You have descended without noticing the descent. The way sleep deepens without the sleeper registering each stage of its deepening. The crinoid meadows below are visible not as individual organisms, but as a textured surface. A carpet of slow biological motion. Each stalk and arm indistinguishable from its neighbors at this distance. The whole forming a continuous living layer between the rock of the seafloor and the open water of the mid-depth zone. The temperature has dropped. Not dramatically, but measurably. The warmth of the surface layer is a memory here rather than a present reality. The water carries the temperature of depth, not the extreme cold of the abyssal zone, which is far below. The stable, unhurried cool of the lower shelf. The kind of cool that does not change with the season. That does not respond to the temperature of the day above the surface. That has been the same temperature, within a degree or two, for longer than any individual organism in this ocean has been alive. Your body has adjusted to it. You are not cold, you are simply cooler than you were. And the coolness has a quality that is not unpleasant. It is clear, it is consistent, it asks nothing of you. It simply exists, pressing evenly against every surface of your body from every direction simultaneously. Breathe. The water around you carries the sound of the Permian Ocean. In the same way a seashell carries the sound of any ocean, not literally, but as a resonant memory. The low-frequency vibration beneath everything is more present here. It does not have a source you can identify. It is simply in the water, the sound of geological scale, the sound of a planet being a planet. The sentences are shorter now. The thoughts come more slowly. This is correct. This is the right pace for this depth. We are no longer visitors, observing from a comfortable distance. We are here in the Permian deep shelf, in the permanent dimness, in the company of things that have never known the surface and have no need of it. And Helicoprion is close, closer than it was before. You have seen the shadow. Now see the animal. The largest confirmed Helicoprion individuals reached approximately 7.5 meters in total length. Some paleontologists extrapolating from the proportional size of particularly large tooth whorls, suggests that exceptional individuals may have reached 9 meters or beyond. These larger estimates are speculative. Without skeletal material, without the cartilaginous framework that would anchor the tooth whorl in a known anatomical position, the extrapolations carry significant uncertainty. But 7.5 meters is confirmed. 7.5 meters is enough. To put that length in terms that occupy physical space in your imagination, 7.5 meters is the length of a large SUV and a pickup truck parked end to end. It is the height of a 2-story building. It is longer than the wingspan of a small aircraft. It is the distance covered in approximately 9 walking steps. In water, length translates differently than on land. A 7.5-meter animal moving through water displaces a volume of water equal to its own body volume with every movement. The pressure waves generated by its passage travel outward in all directions at the speed of sound in seawater, approximately 1,500 meters per second. Every organism within a meaningful radius feels the passage of an animal this size before it sees it. Its weight is estimated, based on body plan comparisons with modern chimeras and large sharks of similar length, at somewhere between 450 and 600 kilograms. Nearly half a ton of cartilage and muscle and organ tissue moving through the water. Slow, continuous pectoral fin-driven glide. The mass of it would have been apparent even at a distance. Not from visual cues alone. The dimness here makes visual assessment of mass difficult. But from the pressure waves, from the displacement of water that moved ahead of it and around it and behind it as it passed. Small fish scattered from its path. Not because they detected aggression. Not because Helicoprion was actively pursuing them. They scattered because something of that mass moving through water at that proximity triggered the pressure-sensing lateral line organs they all possessed. The response to that signal was automatic, involuntary. The bodies of small fish do not wait for conscious processing before responding to the proximity of something very large. They simply move away as fast as the lateral line response allows. Helicoprion moved through a corridor of clearing water. Everything within 3 or 4 body lengths moved aside. And then, when it had passed, everything slowly returned to its previous position. As if the animal were a slow wave moving through the biological fabric of the ocean. Disturbing the pattern, passing through, allowing the pattern to reform behind it. Unchanged. Consider the mathematics of the spiral for a moment. Not the biology, not the feeding mechanics, just the mathematics. The logarithmic spiral, the specific geometric form of Helicoprion's tooth whorl, has a property that mathematicians describe as self-similarity. At any scale, at any point along its length, the curve looks identical to any other point along its length. Zoom in, zoom out, the shape does not change. It is the same curve, at every level of magnification, in every direction from every center point. This property is called a fractal quality. It appears in nature with a frequency that suggests it is not accidental. The spiral of a nautilus shell, the branching pattern of a river delta viewed from above, the spiral arms of a galaxy, the arrangement of seeds in the center of a sunflower, packed in 2 sets of spirals whose numbers are always consecutive Fibonacci numbers. The logarithmic spiral seems to be something the universe returns to repeatedly, across scales separated by orders of magnitude, across biological kingdoms separated by hundreds of millions of years of evolution. across physical processes separated by the entire conceptual distance between biology and physics. Helicoprion's tooth whorl was a logarithmic spiral. It was also, specifically, a record. The tooth whorl of a mature Helicoprion individual contained between 150 and 180 individual teeth. Each tooth was formed at the center of the spiral, the newest, innermost position, then pushed progressively outward as new teeth formed behind it. The teeth did not shed. They were not replaced individually, the way the teeth of a modern shark are replaced. Sharks produce multiple generations of teeth throughout their lives, losing and replacing each tooth many times. Helicoprion produced one generation of teeth, one spiral, one continuous record of every year of its life, mineralized and preserved in perfect geometric order. The outermost teeth, the oldest ones, curved away from the jaw entirely. They no longer made contact with prey during feeding. They had retired from active function, pushed outward by the growth of newer teeth beneath them. Preserved in the spiral like the earlier chapters of a book that the reader has moved beyond, but that remain in the binding. The innermost teeth, sharp and new, still carrying the precise geometry they were formed with, handled all active feeding. The intermediate teeth, partially worn, still partially functional, occupied the middle range of the spiral. Together, these three zones of the whorl created a continuous spectrum from new to old, from sharp to smooth, from functional to archived. Scientists who have studied Helicoprion tooth whorls in detail have counted individual teeth with precision. The CT scan data from the 2013 Idaho study allowed researchers to count 117 individual teeth in that specific specimen's whorl. They observed that many of the outermost teeth were worn in specific ways that indicated contact with hard material. Calcium carbonate shell, ammonoid shell. The wear patterns on individual teeth preserve, in microscopic detail, the dietary history of a specific animal across the entire span of its life. Every meal, written in wear marks on mineralized teeth, arranged in chronological order from outside to inside. The tooth whorl of Helicoprion was a biography, written in the language of calcium and geometry and time. Close your eyes in the Permian Ocean. Not metaphorically, literally within this visualization, allow the visual component to fade. The green-gray opacity, the crinoid meadow below. The diffuse, sourceless illumination of the deep shelf. Let it go. What remains when the visual world is removed is the sensory world that Helicoprion actually inhabited. Because Helicoprion, in the silty, particle-laden water of the Permian deep shelf, was not primarily a visual predator. Its eyes, reconstructed from the orbit sizes preserved in the few specimens that include partial skull material, were moderate in size. Functional, capable of detecting light and shadow and broad shapes at close range. But not the dominant sense. The dominant sense was electric. All cartilaginous fish, sharks, rays, chimeras, and their relatives possess a sensory system called the ampullae of Lorenzini. Small, gel-filled canals in the skin of the head connect to sensory cells. These cells can detect extremely weak electrical fields, the fields produced by the muscle activity of living organisms, by the movement of ions across cell membranes, by the electrochemical activity of life itself. In clean water, a modern shark can detect electrical fields as weak as 5 billionths of a volt per centimeter. This is a number so small it has no intuitive meaning. It is, practically speaking, the electrical equivalent of a whisper heard from across a quiet room. It is the electrical signature of a fish's heartbeat at a distance of a meter or more. Helicoprion almost certainly possessed this system, or its evolutionary equivalent. Moving through the Permian shelf water, it would have experienced the electric world as a continuous field of signals. Background noise from the minerals dissolved in the seawater, constant, unchanging, filtered out by the nervous system. The way human ears filter out the constant sound of ambient room noise. And embedded within that background, the signals of living organisms. The slow electrical pulse of a resting ammonoid, drifting in the current 2 meters ahead. The stronger, more irregular signal of a small fish actively swimming nearby. The very faint signal of a brachiopod on the seafloor below, its filtering arms moving in the current. Each signal arriving at the ampullae on different sides of the head at fractionally different times. And from the differential in arrival time, the nervous system computing the direction and approximate distance of the source. Navigation by electricity. Predation by electricity. A world perceived not as light and color and shape, but as a continuous, three-dimensional map of electrical activity. Every living thing within range broadcasting its position, its activity level, its behavioral state. All of it visible to the right sensory apparatus, all of it invisible to the organisms producing it. Now add the lateral line. The lateral line is a system of fluid-filled canals running along the sides of the body and across the head of fish and many aquatic amphibians. The canals contain hair cells, mechanoreceptors sensitive to changes in water pressure and water movement. They detect the pressure waves generated by other animals moving through the water. The displacement of water molecules as a swimming fish passes nearby. The turbulence generated by a struggling prey organism. The bow wave of a large animal approaching from ahead. Helicoprion's lateral line would have given it a detailed picture of water movement in all directions simultaneously. Together, electroreception and lateral line, Helicoprion navigated a sensory world of extraordinary richness. Not the visual world of daylight and color and distance, a closer world. A world of pressure and electricity, and the patient accumulation of tiny signals into useful information. A world that exists everywhere around every living thing. Invisible, continuous, informative. The world of the deep, perceived by something perfectly built for perceiving it. Helicoprion was almost certainly alone. Not lonely. Alone in the way that solitude is a strategy rather than a condition. In the way that many large predators in every era of Earth's history have been solitary. Not from any absence of social capacity, but because the mathematics of large predator ecology makes solitude more efficient than grouping. A large predator requires substantial food intake to sustain its body mass. In an environment where prey is distributed across a wide area, two large predators hunting the same area will quickly deplete the local prey population. They will be forced to range further for the next meal. One large predator hunting the same area can sustain itself indefinitely, if the area is large enough and the prey population sufficient. The territory of a solitary Helicoprion individual would have been large, not defended in the aggressive, territorial sense of some vertebrates, not patrolled with explicit boundary-marking behavior, but large in the sense of the area an individual needed to range across to encounter sufficient prey. Comparable, perhaps, to the home ranges of modern large sharks, which can span hundreds or thousands of square kilometers of ocean over the course of a year. Within that range, the animal moved continuously. Not frantically, not urgently. With the patient, continuous motion of something that has nowhere specific to be and everywhere generally to go. There may have been exceptions to this solitude. Modern chimeras, the closest living relatives, aggregate in certain circumstances. Near spawning grounds, where individuals congregate for reproduction, solitary animals briefly become social ones. The aggregation is temporary. It serves a specific purpose. When the purpose is complete, the individuals disperse again into their separate ranges. Helicoprion likely reproduced in a similar way, laying eggs in cases, as chimeras do, in specific substrate types that provided the right conditions for development. The eggs of modern chimeras are enclosed in tough, fibrous cases that anchor to the seafloor or to reef structure. The embryo develops inside the case over a period of months, nourished by a large yolk. When development is complete, the juvenile emerges, small, fully formed, immediately independent. There is no parental care. There is no family unit. The juvenile Helicoprion emerges into the Permian Ocean already equipped with its electroreceptive system, its lateral line, and the earliest coils of what will eventually become its fully developed tooth whorl. It is immediately a predator, though a small one. It hunts the smallest ammonoids, the smallest soft-bodied invertebrates. It is itself prey for larger fish during this early period. Vulnerable in a way the adult will never be. If it survives the juvenile stage, which many do not, it grows. Slowly, continuously, adding length to its body, and coils to its spiral and years to the archive written in its teeth. It grows until it is large enough that nothing in the Permian Shelf ecosystem views it as a viable prey item. And then it continues to grow beyond that point. Because growth in fish does not necessarily stop at a particular size threshold. Many cartilaginous fish continue growing throughout their lives, simply at a slower rate as they age. The largest individuals in any population are often the oldest ones. The animal that reaches 7.5 meters may be doing so after many decades of continuous, slow growth. Decades of patient ranging through the shelf water, decades of meals, decades of solitude. Alone in the way the ocean is alone. Complete in itself. Settled toward the seafloor. Not all the way to the seafloor. Stay in the water column, perhaps 5 meters above the crinoid carpet, and simply observe. The reef structure here is not the vivid, dense, visually overwhelming architecture of a modern tropical coral reef. There are no vivid colors. There is no riot of competing shapes and sizes. The Permian Reef is quieter than that, more austere, more patient in its construction. The dominant framework builders are bryozoans, colonial animals. Each individual organism in a bryozoan colony is tiny, almost microscopic. Together they construct branching, calcified structures of surprising size and complexity. The individual branches are finger-thick or thumb-thick, pale in color, ranging from cream to gray to a faded amber. They extend outward from their attachment points on the hard substrate below. Rock outcroppings, the shells of dead brachiopods, older bryozoan structures that have died and calcified into reef framework. They branch in patterns that carry their own geometric logic. Between the bryozoan branches, sponges. Many kinds of sponges. Some encrusting, flat, spreading sheets of sponge tissue coating available hard surfaces in muted purples and grays and yellows. some erect, tall, vase-shaped sponges standing a half-meter or more above the seafloor. Their filtration chambers draw a slow, continuous current of water through their porous walls. Some silicious, built from interlocking spicules of silica that form delicate three-dimensional lattices of extraordinary geometric precision. The sponge reef filters the current. Every liter of water that passes through this community passes through countless filter-feeding structures. Each one removes particles of organic material from the water and converts them into sponge tissue. The community is a slow, continuous food processing system operating at enormous scale. Water enters the reef zone carrying suspended particles of organic material. Water leaves the reef zone stripped of much of that material. The difference the organic matter removed has become reef biomass, has become sponge and bryozoan and crinoid tissue, has become the base of the food pyramid that Helicoprion sits at the top of. This connection is not metaphorical, it is literal and traceable. The sponge community filters organic particles from the water and grows. Small invertebrates graze on the sponge community and grow. Small fish feed on the small invertebrates and grow. Ammonoids feed on the small fish and on the zooplankton and grow. Helicoprion feeds on the ammonoids. And the energy that sustains Helicoprion's 7.5-meter body began, ultimately, in the photosynthesis of phytoplankton at the ocean's sunlit surface. The connection between the surface and the deep runs through every organism in between. A chain of energy transfer so long and so complex that no individual link in it could recognize its position in the whole. Helicoprion drifts above this reef community now. It is not actively hunting at this moment. Its electroreceptors sweep the water. Nothing within immediate range registers as worthwhile prey. The crinoids below signal their presence as a continuous low-level electrical murmur. Alive, but not the kind of alive that Helicoprion's sensory system categorizes as food. The animal maintains its depth above the reef with minimal fin adjustment. Its body is still. Its tail makes one slow sweep, then holds, then sweeps again. The crinoids below extend their arms into the current. The bryozoan branches reach their steady, patient reach toward the water above them. The sponges pull their endless slow current through their porous walls. Everything is occupied. Everything is doing exactly what it has always done. The permanence of it, the sense of a community that has been operating in essentially this same way for millions of years and will continue operating in this same way for millions more, has a quality of stillness that is deeper than any physical stillness. The stillness of things that have found their form and no longer need to search for it. Nothing is invulnerable. The adult Helicoprion, 7 meters, half a ton, equipped with its electroreceptive sensors and its spiral jaw and the hydrodynamic efficiency of a body shaped by millions of years of selection, had no known predators. Nothing in the Permian Shelf ecosystem has been identified that could have regularly taken an adult individual as prey. But invulnerability to predation is not the same as invulnerability. The juvenile Helicoprion was vulnerable for years. Before it reached the size at which it became effectively prey-proof, it moved through the Permian Ocean as a small, fast-growing, soft cartilaginous animal. Larger predators would have taken it opportunistically. The years between hatching and reaching significant size were years of relative danger, of staying close to reef structure, of hunting small prey in environments that offered some protection from larger animals. of growing as fast as biology allowed. The mortality rate among juveniles was almost certainly high. This is true for virtually every large marine predator across the history of life. High juvenile mortality offset by long adult lifespan. The few individuals that survive the vulnerable early years become the large, long-lived, effectively predator-proof adults that define the species in our imagination. But even the adults faced biological challenges. Parasites were almost certainly present. Cartilaginous fish today carry a range of external and internal parasites. Copepods and monogeneans on the skin and gills, various helminths in the digestive system. The immune systems of cartilaginous fish are sophisticated. They possess adaptive immunity, unlike many invertebrates. But they are not perfect. Parasite loads can affect feeding efficiency, movement, and ultimately survival. Injury was a possibility. The Permian Shelf was a densely populated environment. Encounters with other large animals could result in injuries to fins, to the skin, to the gill arches. A damaged pectoral fin changes locomotion efficiency. Changed locomotion efficiency changes foraging range and feeding success. Reduced feeding success over extended periods means reduced energy for growth and immune function. The chain of consequence from a single injury could, in the wrong circumstances, propagate through months or years of the animal's life. And then there was the deeper challenge. The challenge that no individual adaptation could address. The challenge of finding enough prey. The Permian Ocean was productive, enormously productive by any reasonable measure. But the prey populations of any ecosystem fluctuate with the seasons and with longer period cycles of oceanographic change. Warm periods bring high productivity. Cooler periods or periods of changed current patterns bring lower productivity. Lower productivity means fewer ammonoids in the water column. Fewer ammonoids means longer search times and lower feeding success for Helicoprion. During lean periods, the animal did what large, slow predators have always done during lean periods. It slowed down. It reduced its metabolic rate as much as possible. Spent more time at depth where the temperature was stable. Made fewer movements, covered less distance. Waited for the productivity cycle to turn. There are probably places in the Permian Ocean, specific depth zones, specific current shadow areas, where large Helicoprion individuals spent extended periods of relative stillness. Hovering in the cool, opaque water. Barely moving. Conserving. Waiting. The electroreceptors still swept the water even during these periods of stillness. Because the electroreceptive system requires no active effort, it is always on, always monitoring, always ready to redirect the animal's attention toward the electrical signature of something worth pursuing. Even in stillness, Helicoprion was never entirely still. It was searching. Always searching. 10 million years. Perhaps 15. Allow those numbers to settle into the same place in your awareness, where you have been receiving the information about the Permian Ocean and the animal that moved through it. Let them settle slowly, the way sediment settles slowly through still water. Not dropped, not placed, but drifting into position under the gentle, constant pull of their own weight. 10 to 15 million years of Helicoprion in the Permian Ocean. During that span of time, the human species will have risen and risen again approximately 50 times, if our current trajectory holds. The entirety of human recorded history, writing, mathematics, philosophy, architecture. Every war and every treaty and every scientific discovery from the first clay tablet to the last server farm will have occurred 15 times over within a single Helicoprion lineage's span of existence. The animal was not aware of its own persistence. It had no concept of duration, no sense of its place in geological time, no knowledge that it had outlasted dozens of other species that came into being and vanished, while it continued to move through the same water in the same patient way. It simply continued, because the conditions for continuation existed. The water was warm enough, the prey was sufficient, the body plan was efficient, the jaw mechanism worked, the electroreceptive system worked. The reproductive strategy produced enough viable juveniles to maintain population numbers. Every component of the animal's biology was adequate to its environment. And adequacy, in evolutionary terms, is all that is required for persistence. Not excellence, not optimization, not the best possible version of any given trait. Adequacy. Helicoprion was adequate to its environment for 10 to 15 million years. Then something changed. Not quickly, not in any way that the animal could have detected, even with its extraordinary sensory equipment. The change began far away, deep in the crust of the earth, beneath what would eventually become Siberia. In a geological structure we now call the Siberian Traps, a region of the Earth's crust that was, in the late Permian, experiencing one of the largest volcanic events in the history of the planet. The eruptions were not like any volcanic event in recorded human history. They were not individual volcanoes, not mountain-building events with defined peaks and discrete eruption episodes. They were flood basalts, vast sheets of magma welling up from the mantle and spreading across the surface of the earth in rivers, and then seas of liquid rock, covering an area of the planet's surface estimated at approximately 2 million square kilometers, roughly equivalent to the entire landmass of Western Europe, in layers of basalt a kilometer thick in some places, and releasing, in the process, quantities of carbon dioxide and sulfur dioxide into the atmosphere that had not been seen since the dawn of complex animal life. The ocean above this change did not know yet what was coming. The water was still warm, the crinoids were still swaying, the ammonoids were still spiraling through the midwater column. Helicoprion was still moving through the water, still searching, still completely, serenely, biologically unaware that the world it had been built for was beginning, very slowly, to end. The transition to the final layer is upon us now. The water around you is not yet different, not yet. But something has changed in the quality of the silence. Something in the way the low-frequency hum beneath everything carries, now, the faintest suggestion of a different note. Something ending, something settling, like sediment falling slowly through still water. Down, down, into the dark. The water is the same. This is the first important thing to understand about what is coming. The water does not change overnight. The ocean does not announce its transformation with any signal that any organism alive within it could detect and respond to. There is no moment, no single morning, no single season when the Permian Ocean becomes visibly, measurably different from what it was the day before. The change is slower than that. Far slower. It moves at the pace of chemistry, at the pace of gas dissolving into water across an ocean surface that covers most of the planet, At the pace of degrees, not degrees per day, not degrees per year, but degrees per 1,000 years, per 10,000 years. Increments so small that the lifetime of any individual organism, even an organism as long-lived as Helicoprion, would register only a fraction of a single degree of change. The Siberian traps are erupting. They have been erupting in pulses for what will eventually total approximately 1 million years. The volumes of material involved are geological in scale. They are beyond the capacity of any ordinary frame of reference to hold. Millions of cubic kilometers of basalt, billions of tons of carbon dioxide released directly into the atmosphere from the magma itself. And again from the carbon-rich sedimentary rocks, the magma passes through on its way to the surface. The atmospheric concentration of carbon dioxide rises, slowly, persistently, without pause. The greenhouse effect strengthens. The planet warms. And the ocean, which covers most of the planet's surface and exchanges gases with the atmosphere across that entire surface continuously, absorbs carbon dioxide from the warming air above it. This is where the ocean begins to change. Carbon dioxide dissolving in seawater does not simply disappear into the water and become inert. It reacts. It combines with water molecules to form carbonic acid. A weak acid, not dramatically corrosive, not immediately destructive to anything large and mobile, but persistent. And in sufficient concentration, consequential. The pH of the Permian Ocean begins to drop. By fractions of a unit, then by tenths of a unit. Then, over tens of thousands of years, by amounts that begin to affect the organisms whose biology depends on maintaining a specific chemical relationship with the water around them. The organisms most immediately affected are the ones that build their structures from calcium carbonate. Calcium carbonate, the mineral that forms the shells of brachiopods, the shells of ammonoids, the skeletal material of bryozoans and many sponges, is soluble in acid. Mildly acid, weakly acid, the kind of acid that the ocean is becoming. At first, the effect is subtle. Shell growth rates slow slightly. Shells that would have been a certain thickness become slightly thinner. Juveniles that would have survived a minor injury to their shell do not. The shell is no longer robust enough to protect the tissue beneath. Small changes, invisible changes, changes that no individual organism in the Permian Ocean can detect or respond to, but changes that compound, generation over generation over generation. The water is still warm, the crinoids are still swaying, but the brachiopod populations on the seafloor are slightly thinner than they were 10,000 years ago. The bryozoan reef is slightly less dense. The sponge community is slightly less productive. Slightly. Only slightly. For now, the ammonoids are struggling. Remember them, the spiraling cephalopods of the Permian midwater. The prey that Helicoprion's entire jaw architecture was built to capture. The organisms whose abundance in the fossil record told us how densely populated the Permian Ocean was in life. Remember the way they moved through the water column, that slow, patient, buoyancy-controlled spiral. The ammonoids are still there, but there are fewer of them. The thinning of their shells, a consequence of reduced carbonate saturation in the increasingly acidic water, has made each individual more vulnerable to predation. Predation rates are the same, but survival rates of attacked individuals are lower. And the juveniles, the tiny ammonoids that should have been recruiting into the adult population in their millions each year, are recruiting in smaller numbers. Because the juvenile shell, the very first coils of the spiral formed at hatching, is the thinnest and most vulnerable. In water whose chemistry has shifted even slightly against calcification, more juveniles are failing before they can grow enough to reinforce their shells. Population growth slows, then stops, then reverses. This process does not happen in a year. It does not happen in a century. It happens across thousands of years. A decline so gradual that a population census taken one generation apart would show almost no measurable difference. A population census taken 10,000 years apart would show a significant one. Helicoprion does not take population censuses. It simply searches. Electroreceptors sweeping the water, lateral line monitoring pressure. The same behavior it has always performed in the same water at the same depth, with the same patient efficiency. But the responses are fewer. The water that once returned the electrical signature of an ammonoid every few minutes of searching now returns that signature less frequently. The intervals between prey detections are longer. The distances Helicoprion must cover to find sufficient food are greater. Its ranging behavior expands. It moves further each day than it once did to encounter the same number of prey items. The energy cost of foraging increases. The energy available from foraging decreases. Because the ammonoids it does find are smaller on average. Their populations are skewed toward younger individuals as recruitment of older, larger animals fails. The predator is being starved by the disappearance of its prey. Not suddenly, not dramatically. By degrees. By the same imperceptible degrees by which the ocean's pH is dropping. By which the atmospheric CO2 is rising. By which the global temperature is climbing. Everything connected, everything in the same slow cascade. And while the prey diminishes, the ocean itself is changing in other ways. The warming of the surface water reduces the temperature differential between surface and deep. This differential drives ocean circulation. In a well-circulated ocean, cold, oxygen-rich water from the poles sinks and spreads through the deep ocean. It maintains oxygen levels adequate for complex life throughout the water column. As the temperature differential decreases, this circulation slows. As it slows, the deep water becomes less oxygenated. Oxygen minimum zones expand. Areas of the ocean that were once habitable for large, active predators become inhospitable. The available habitat for animals with high oxygen demands begins to contract. Animals like Helicoprion, whose large body and active predatory lifestyle requires substantial oxygen delivery through the gills. From below, oxygen depletion. From above, acidification and prey loss. From the sides, rising temperatures pushing the comfortable temperature range toward the poles, compressing the equatorial habitat into a narrower band. The walls are closing in. Slowly, slowly. But closing. There is no way to know, from the fossil record, exactly when the last Helicoprion died. The fossil record does not preserve last moments. It preserves the remains of organism that happen to be buried in the right conditions at the right time. The completeness of any organism's representation in the fossil record is a function of how many individuals existed, how their remains were distributed, and how many of those remains ended up in depositional environments that led to fossilization. As a population declines toward extinction, the chances of any individual's remains being fossilized decline with it. The last Helicoprion left no fossil. Or if it did, we have not found it, and we may never find it. What the fossil record gives us instead is a picture of decreasing representation across the late Permian. Fewer Helicoprion fossils from sediments deposited in the final millions of years before the extinction boundary. Not absence, just less. A thinning of the record that mirrors, probably, a thinning of the actual population. But let us visit that last generation anyway. Not as science, as imagination. As the kind of careful, evidence-grounded visualization that allows us to honor something that existed for 15 million years and left behind nothing but a spiral in stone. The water is warmer than it was. Not dramatically. Not to a degree that a human immersed in it would immediately register as wrong. But warm in a way that carries a slightly different quality than the warmth of the early Permian shallow shelf. A denser warmth, a warmth with less oxygen in it. The gills are working slightly harder to extract the same amount of oxygen from each volume of water that passes through them. The ammonoids are rare now. The Helicoprion moves through water that is largely empty of the prey it was built for. Its electroreceptors sweep wide arcs through the water and return, more often than not, nothing. The intervals between prey detections that were once measured in minutes are now measured in hours. The animal is thin, not visibly, dramatically emaciated. It does not look like a dying animal in any way that an observer would immediately recognize. But its body reserves are lower than they should be. The fat stored in its liver, cartilaginous fish store energy as oil in their livers rather than as subcutaneous fat, is being consumed faster than it is being replaced. It moves. It has always moved. Movement is the primary behavior. The search is the primary behavior. It does not know how to stop searching, because searching is what it is. It is not a decision. It is not a strategy chosen from among available alternatives. It is the behavior of a biological machine executing its programming in an environment that no longer adequately supports the execution. The spiral jaw opens and closes against water that holds nothing. The tail sweeps. The pectoral fins make their small, continuous adjustments. The electroreceptors sweep. Nothing. Then faint, distant. The electrical signature of something small. Smaller than Helicoprion typically pursues. A juvenile ammonoid perhaps, or something else entirely. The signal is faint enough that under normal circumstances, in a prey-rich environment, it would not merit a heading change. Under these circumstances, it does. The heading changes. The tail sweeps quickened by a small amount. The distance closes. The jaw opens. Death for a marine animal is not a dramatic event. There is no visible moment of ending. The biological processes that constitute life slow, gradually, rather than stopping suddenly. The heartbeat becomes irregular, then infrequent, then absent. The muscular tone that maintained the animal's position in the water column fades. The body, no longer actively buoyed by swimming behavior, begins to respond to the pull of its own mass. It sinks, slowly at first. The oil in the liver provides some buoyancy. Cartilaginous fish have no swim bladder, no internal gas compartment for precise depth control. But the low-density oil in an enlarged liver provides passive buoyancy that keeps the animal near neutral in life. In death, this buoyancy is insufficient to counteract gravity. The body tips slightly, one side faces up, the other faces the seafloor. And it descends. not the descent we have been making. The gradual, deliberate, observer's descent into deeper understanding of a deeper time. This descent is different. This is the descent of matter, returning to the seafloor that produced the energy that built it. The closing of a cycle that began when sunlight struck the ocean surface and was captured by phytoplankton. That energy moved through the food web in steps, from phytoplankton to zooplankton to ammonoid to helicoprion, and now moves back toward the seafloor in a single step. Gravity applied to 7.5 meters of cartilage and muscle and oil. The soft tissues begin to disperse before the body reaches the seafloor. Scavengers arrive. They always arrive. The Permian seafloor has its scavengers, just as every seafloor in every era does. Small fish, invertebrates responding to the chemical signal of decaying tissue carried through the water. They are not respectful. They are biological machines executing their own programming. The tissue disappears methodically. The large structural elements are reduced to their constituent chemistry, distributed back into the water column and the sediment below. The cartilaginous skeleton dissolves. This is the nature of cartilage. It was not built to resist the chemistry of decay and the slow dissolution of the seafloor environment. Without the protective processes of a living body around it, it returns to its component molecules within months. Almost nothing remains, except the tooth whorl. The spiral, composed of dentine and enameloid, harder, denser, more chemically stable than any other material in the animal's body, settles onto the seafloor. The last of the soft tissue that connected it to the jaw disappears. The spiral remains. It is roughly dinner plate sized, perhaps slightly larger if this was an older individual. Its outer coils are worn smooth by decades of use. Its inner coils retain the sharp geometry of recently formed teeth. It is pale, almost white against the dark sediment of the Permian seafloor. It does not look like a relic. It does not look ancient. It looks exactly like what it is, a biological structure that has reached the end of its functional life. No longer part of anything living, no longer in motion, no longer searching. Just there, the current moves sediment across the seafloor in thin sheets. The first layer of sediment covers the outermost edge of the spiral. Then the next layer. Then the next. Each layer is thin, composed of the finest particles, clay minerals, the skeletal remains of microscopic organisms, the chemical precipitates of changing ocean chemistry. Each layer is deposited slowly, a millimeter per 1,000 years in some environments, a few centimeters per 1,000 years in more productive ones. The spiral disappears beneath the accumulating sediment. It is very quiet now. It is very still. The sediment continues to accumulate. There is no reason for it to stop. The ocean floor is a surface, and surfaces accumulate material. This is what surfaces do. The material arrives from above, from the constant slow rain of particles through the water column, and from the sides carried by bottom currents. It settles, it compresses under the weight of the layers above it. It begins, over geological time, to lithify, to convert from loose sediment into solid rock, as the water is squeezed from the spaces between particles. Mineral cements crystallize in the remaining pores. The spiral, buried beneath meters of compacting sediment, is compressed. The pressure is not violent. It does not crack the spiral or deform its geometry. The spiral was built to withstand the mechanical stresses of a jaw closing with significant force. It is, among biological structures, extraordinarily robust. The compression of burial simply holds it more firmly in place, integrates it into the rock forming around it. The spiral becomes part of the Permian limestone. Above it, the extinction event reaches its maximum intensity. The end Permian mass extinction, the one we call the Great Dying, eliminates approximately 96% of all marine species. 96%. A number that, like all very large numbers in geology, resists full comprehension. The crinoid meadows are gone. The brachiopod communities are gone. The bryozoan reefs are gone. The ammonoids, reduced but surviving through the extinction boundary as a group, one of the more resilient lineages, are dramatically reduced. They will spend millions of years recovering. The Permian Ocean, above the entombed spiral, ceases to exist as the Permian Ocean. The water remains, the ocean remains. But the community of organisms that characterize the Permian shallow shelf is gone. What replaces it, gradually over the millions of years that follow, is a different ocean. A Triassic Ocean, rebuilt from the survivors, repopulated by the lineages that crossed the extinction boundary, and diversified into the ecological space left by everything that did not. The spiral lies in its rock and does not know any of this. It is not capable of knowing. It is a mineralized structure, a tooth whorl, a coil of dentine and enameloid in pale limestone. But it is intact. While the world above it transforms beyond recognition, while the Triassic Ocean gives way to the Jurassic, and the Jurassic to the Cretaceous, and the Cretaceous is itself ended by an asteroid impact that kills 3/4 of all species on Earth, while the first mammals grow larger and the first birds learn to fly, and the first primates climb into the first trees, while the continents drift apart from their Pangaean configuration into the arrangement that will eventually be recognizable as the modern world, the spiral lies in its rock. Still, patient in the way that only objects can be patient, without any experience of patience, without any experience of duration, without any awareness of the extraordinary journey the tectonic plate beneath it is making. Slowly, over hundreds of millions of years, carrying the limestone and the spiral embedded within it northward and eastward across the surface of the Earth. From somewhere near the equatorial margin of ancient Pangaea, toward what will eventually be Idaho. The mammals diversify, the primates develop larger brains. One lineage of primate develops language, and then writing, and then mathematics. Then the ability to recognize, in a particular pattern of pale curves in pale limestone, the fossilized remains of something that lived 250 million years before them. The spiral waits. It has nowhere to go. It has no reason to hurry. It simply waits, in the way that stone waits, without waiting, without any sense of time passing, without anything at all except the geological fact of its continued existence. Intact, unchanged, still perfectly, precisely, logarithmically spiral. The limestone erodes. This too is slow. This too is geological in its pace, but erosion is persistent. Water finds cracks in rock and freezes and expands and widens the cracks. Wind carries abrasive particles against exposed surfaces and grinds them away particle by particle. The chemistry of rainwater, slightly acidic from dissolved carbon dioxide, the same chemistry that helped end the Permian Ocean, dissolves the surface of the limestone incrementally. The cliff face retreats. Year by year, millimeter by millimeter. The surface of the rock was buried under hundreds of meters of subsequent sediment. then uplifted by tectonic forces, then exposed by erosion to the dry air of what is now the American West. That surface retreats toward the spiral. And one year, some year in the late 19th century, some dry summer afternoon with the smell of sage and warm rock in the air, the retreating limestone surface reaches the outermost coil of the spiral. It is exposed. A curved line of slightly different texture and slightly different color appears in the face of the cliff. Then another curve parallel to the first. Then the arc of the outermost coil becomes visible, pale and smooth against the gray-brown limestone matrix. It waits there, in the cliff face, in the dry Idaho air, in the sunlight that is so different from the Permian shelf light that once filtered down through 30 meters of ancient seawater. It waits until someone comes, until a human being, a geologist, a prospector, a rancher walking a fence line, we do not know precisely who made the first observation, sees the spiral in the rock and stops, and understands that it is significant without, yet understanding what it is. The fossil is collected, it travels, it reaches the hands of researchers. It is examined, described, named Helicoprion spiral saw. The long debate about where the spiral belonged begins. The drawings proliferate, the theories multiply. And the spiral, patient, intact, unchanged, submits to each examination with complete indifference. It has been in the rock for 250 million years. A researcher's brush and a CT scanning machine are not remarkable by comparison. What is remarkable is that it is here at all. That the one structure in the entire animal hard enough to survive the chemistry of the seafloor, and the pressure of burial, and the heat of deep lithification, and the slow journey of tectonic transport across 250 million years of Earth history, that structure happened to be the most extraordinary, the most geometrically precise, the most biologically unusual structure in the animal's entire body. Not a vertebra, not a scale, not a fin spine. The spiral. As if the animal chose, in dying, to leave behind the one thing that would guarantee it would never be forgotten. As if the geometry insisted on being remembered. It is beautiful. In the dry Idaho air, in the pale limestone, in the cool light of a museum display case in Pocatello. Still beautiful, still precise, still perfectly, logarithmically, impossibly spiral. The ocean floor holds the memory of every giant that ever fell. Not in language, not in image. In chemistry and geometry, and the slow, patient conversion of biology into stone. In the shapes of things preserved in rock. Not all things, not even most things, but the things that were hard enough and dense enough and fortunate enough in their position and their burial to survive the extraordinary journey from life to fossil. Helicoprion survived that journey. A spiral in pale stone. A coil of 180 teeth arranged in a perfect logarithmic curve. The biography of an animal written in calcium and reed, 250 million years later, by the light of a CT scanner in a museum basement in Idaho. It lived for 10 to 15 million years in a warm, green-gray ocean that no longer exists. It moved through that ocean with the patient, electroreceptive efficiency of an animal perfectly suited to its world. It ate, it grew, it added tooth after tooth to its spiral. It ranged across a superocean so large that no modern body of water offers a meaningful comparison. And then the ocean changed, and the prey disappeared, and the animal continued searching. In the way that biological machines continue executing their programming, even when the environment that shaped that programming has ceased to exist. Until it stopped. Until the body sank. Until the spiral settled into the sediment, and the sediment became stone. The stone traveled, over 250 million years of tectonic time, to a cliff face in Idaho where it waited in the dry air for someone to come and find it. You have been in the Permian Ocean tonight. You have felt the weight of ancient water, the cool, mineral-rich pressure of a sea that predates every living thing on Earth today. You have seen the shadow move through the green-gray dimness. You have watched the spiral jaw open and close against the soft bodies of creatures that have not existed for 250 million years. You have been a witness to something that asked for no witness, that had no awareness of being witnessed, that simply lived and moved and searched and fell. As everything falls, as everything eventually becomes sediment, and sediment becomes stone, and stone becomes, if it is patient enough, a memory. Let the memory settle now. Let it sink through the water, the way particles sink through still water. Slowly, without urgency, finding their resting place at the bottom of things. Let your body find its resting place. Let the Permian Ocean hold you. It is very good at holding things. It has been holding this spiral for 250 million years without once letting go. Rest now. The water is still. The crinoids have stopped swaying. The ammonoids have drifted below the range of visibility. The shadow is gone. Only the spiral remains. Perfect. Precise. At rest. The ocean floor holds the memory of every giant that ever fell. But Helicoprion was not the only titan to vanish into the sediment of deep time. In the next entry, we will explore another creature of the ancient sea. One that lurked in the shadows of the Devonian Ocean, 150 million years before Helicoprion drew its first breath. An animal so large, so heavily armored, so completely unlike anything alive today, that the ocean it lived in seems almost designed around its presence. A world separated from the surface for far longer. The deep remembers. It always remembers.